We're going to focus on the following points today. Recall that electric current is carried by discrete charge carriages. So we want to know the difference between electron flow and conventional current. We actually even know what current is. It's just the flow of charge or the movement of charged particles. And we want to describe the flow due to an electric potential difference between 2 points on a conductor. And we want to describe the formula used to calculate current and also solve problems involving current, charge, and time. And so let's have a first look at the definition of current, okay? The flow of charge. So here is an image here which shows if we have a potential difference, so we have a negative charge here and a positive charge there, or even if there's just some difference in charge, it's going to give the electrons a repulsion force or an attraction force. It's going to give the electrons some energy, so we call it an electromotive force. Anytime a potential difference gives the electrons energy, we use the word electromotive force. So this is a copper wire, so it has lots of free valence electrons, and so these electrons will start to flow. Okay. Now, how do we measure current? Is we use this triangle. All right. So charge, current, and time. And what we see is that if we want to find charge, we cover it up, and that's going to be current times by time. If we want to find current, that's going to be charge divided by time. And if we want to work out time, we can work out charge divided by current to work out how much time it's been flowing. Okay, so here, if we're focusing specifically on current, what we see is that current I is equal to change in charge over the change in time. And you notice that I added this change in value because it really is a change in charge, because there's already a charge there, but it's the change in charge that makes it a current because it's moving. Now here's a little bit of a thought experiment for you. Draw a diagram and really think about this. What would happen if this wire was not connected to anything else? Would electrons keep piling up on the right hand side? So pause the video, draw a diagram, think about it, and come back and listen for my explanation. So hopefully what you realized is that once these electrons pile up on one side, we get this big negative value here, or negative charges here, okay? And that's going to create an electric field, all right? And so it's going to balance out. So these positive charges here, they can't do anything. These electrons can't go anywhere because the positive charge is outside the conductor. So if I'm an electron here, as I come closer to these electrons as a large charge, I'm going to say, well, no, I don't want to go in that direction. I'm actually going to get repelled in the opposite direction. So the electrons will have an even distribution. Well, not an even distribution, but they will get less and less as they go along, okay? But we form a bit of a capacitance here. So we're going to have the positive charges on this side, okay, and the negative charges on that side. But if they have nowhere to go, they can't flow. So they keep piling up until a certain level, and once they reach a certain level, okay, the electrons start getting sent back in the opposite direction. Okay, but as soon as you could connect it to something, okay, say we connect it to a lead here, all right, and what we have is some sort of way of collecting the electrons that they would flow around here. They would come inside here and they would stay here, okay, then the electrons will flow around the whole circuit and create a circuit. But if they're not connected to everything, if they don't have a full circuit, now this is like a battery, okay, or a power source. The electrons are collected and returned back to Earth, or the electrons are connected and returned back to the electrolytes inside of the battery, okay, and we spoke a little bit about batteries last time. So this is a good diagram of what I was just talking about. So closed circuits have current. So here's your battery, okay, this is the positive terminal, yeah, and this is the negative terminal, and so electrons would be flowing towards the positive terminal. So there'd be electrons flow through here, and the light bulb will be lit up because there'd be electrons flowing through their little filament. And when it flows through the little filament, creates heat energy, and heat energy then creates light energy, and that's why we have a light bulb. But if that circuit was open at the top here, what would happen is that, as we discussed before, electrons would flow around here to start with, and then they would start piling up. And any electron that would come around here would say, oh, well, there's a negative a negative charge at the top there, so I'm just going to go back in the opposite direction. So we get no flow of current. It's actually called a capacitance. Okay, capacitance is a separation of charge. And so this is a good example. So a bird can sit on a power line for as long as it wants. It's not going to, no current's going to flow through the bird. Okay, but growing up in Queensland, Australia, we always saw these bats getting burnt by these power lines, is because their wings were long enough to touch two power lines. And as soon as they touch two power lines, these circuits here have extremely high voltages. And so an extremely high current would pass through the bat, shock it, kill it, burn it, whatever it is. Okay, but that's an example that you can sit on a closed circuit, touch a closed circuit as much as you want, but as soon as you provide a path to another circuit or to the ground, we get a flow of charge. Okay, now conventional current is the flow of positive charge carriers. But after a while, we realized, well, we being scientists realized that it's actually the electrons carrying the charge. And so on this is a circuit diagram here. Okay, the smaller terminal represents the negative. Okay, and the positive terminal represents is the longer line. The positive terminal is called a cathode, and the negative terminal is called an anode. So by convention, we show that current is going in this direction. So the arrow here showing this direction, that's positive current, but it's actually the electron flow going in the opposite direction. Now, here's a good thought experiment. Yeah, what if you considered the electrons frame, that's written wrong, reference frame. So if you're in the electron frames and you considered that to be at rest, what would be happening to the positive charge values? So if I was an electron here moving around, but I would consider that as rest, I would actually be seeing positive charges going in that direction, wouldn't I, as I moved along? If I said that I was moving, but I was at rest, and it was the positive charges moving, then it would look like the positive charges were going in this direction. And that's kind of like if you're sitting at a station and a train starts moving, it sometimes feels like, well, the train is moving. But it's not you, it's the train next to you that's moving, and it just depends on which reference frame you consider. So how do we measure current? Okay, current is measured using an ammeter. Okay, now ammeters are different to voltmeters in terms that, well, one, they measure current, but two, they have to be connected in series. And by in series, that means it has to be connected, okay, so that all the current in a wire is going to be flowing through it. If I do a voltmeter here, okay, a voltmeter potentially has infinite resistance. So no current wants to flow this way, all the current chooses to go through the lamp. Current will naturally want to take the easiest route, okay? So when we call a short circuit, current always takes the shortest circuit or the easiest circuit. So if the voltmeter has a very high resistance, we haven't spoken much about resistance, but we'll get there, then it would flow through it. Whereas an ammeter has zero or negligible resistance, so the current's happy to pass through it. So it's connected to the same wire in series. Now, how does an ammeter work? Anytime there's a flow of charge, there's a magnetic field, okay? And this is obvious here by using metal. They can show you the magnetic field can pull that metal needle in whichever direction, or depending on how much current is flowing through. Obviously, the stronger the current, the more magnetic field created. So how can we look at that? What is actually happening with the current? Okay, so current is going to be the number of electrons or charge carriers. So it could be the number of molecules or ions depending what's flowing the charge, but usually it's electrons multiplied by the charge on that particular charge carrier divided by time. So the total charge is the number of charge carriers times by the value of that charge on the charge carriers, which is usually the number of electrons times by the elementary charge, negative 1.6 times 10 to the negative 19, divided by some time. And we need to use this formula to calculate different currents. Here's a worked example where we have to do just that. So using the formula I equals QT, calculate the number of electrons that flow past a particular point each second in a circuit that carries a current of 0.5 amps. So rearranging the formula to work out what the total charge is, because if we work out the total charge, we can work out the total number of electrons. So the current is 0.5 and T is each second. So the total charge flowing through this circuit is 0.5 coulombs. Now, how many electrons flow through there each second? We take that total charge, 0.5, divide it by negative 1.6 times 10 to the negative 19, and you get that we have 3 times 10 to the 18 electrons. Okay, electrons are abundant in all metals, especially all conductors that are used in electrical circuits. So this is an extremely large number, very normal for the amount of electrons flowing through a particular point in the circuit every second. There is an extreme amount of those. So here's one for try it for yourself. Calculate the number of electrons that flow past a particular point each second in a circuit that carries a current of 0.5 amps. Pause the video, come back and see if you are correct. So very similar to the last example, we want to work out the total number of electrons. And so I'm going to use a different formula here. I might just change my pen color. I'm going to use the one I showed you that combines it all, and that was I was equal to N number of electrons over time. And what we know here is we want to work out the number of electrons, so we get that is going to be IT over E. Okay, so in this particular case here, the number of electrons is going to be I, which is 0.5 amps, which is quite a lot of current, multiplied by 1 second, divided by 1.6 times 10 to the negative 19. And what we see here is that the answer is 4.6875 times 10 to the 18 electrons. Now, we have to be very careful here with the significant figures. They want it in 2 significant figures because this is what's given to us. So we would round that to 4.7 times 10 to the 18 electrons. Be very careful with those significant figures. And that's the answer to that question. All right, so drift velocity. Okay, this is not a difficult concept, but a strange concept, especially when you learn it for the first time. So drift velocity is the actual speed at which electrons are moving. So consider for a second, you're standing in a dark room and you flick the light switch and the light comes on almost instantly. And it's not because that the electron has gotten from the light switch up until the light so quickly that it works. It's actually the speed of an electric field spreads very quickly, and it's different in different substances, but in copper wire, the electric field spreads at a rate of 95% of the speed of light, which is extremely fast. So even if we have let's just draw a picture here of a light switch. So if this is my switch over here, and we draw switches like this in a circuit, open circuit, okay, and then around here I have my light bulb, which we can usually draw as just a simple cross. And I forgot to have my power source, which we can put in here. So if I turn the switch on over here, if I make it shut, okay, It's not that an electron's going to zoom around really fast to that particular light bulb. It's just that these electrons here, there's electrons all throughout this conducting wire, okay? They are going to be the ones that start moving, these ones right next to it, okay? And there's lots of different analogies for this. So one's like a garden hose. If you have a hose and you turn it on, okay, water comes out straight away. That's because there's already water in the hose ready just to be pumped out, and the pressure distributes quickly, okay? And so we have this idea, well, actually, how fast are the electrons actually moving? We call that the drift velocity. Now, in the QCAA course, it doesn't seem that you have to use or have to find the drift velocity of different situations. Okay, what they say is that on average is about 1 millimeter per second, which is quite slow when you think about it. So if you're standing usually at a light switch and you turn the light on, it usually has to pass through about 3 meters as an approximate, as an average, 3 meters of wire before it gets to the light bulb itself. So 3 meters, each meter has 1,000 millimeters. So we're looking at 3,000 seconds before an electron gets from the light switch to the light. And that's, yeah, as I said, is a strange concept for you to think. So the electrons are not zipping through there, but they're moving in abundance, okay? Large current isn't due to the extreme speeds. It is due to the extreme abundance of electrons in conductors, okay? But I think we can do a little bit more on drift velocities. And we're going to have a look at a drift velocity derivation now. And we can consider a current passing through a specific conductor. So here's our conductor. And this is some really interesting physics, and that's why I'm going through it. And, okay, we have electrons on this conductor. Okay. Now, first things first. There are different electrons with different charge conductors. Charge densities. Okay, so charge density. Charge density is the amount of charge or amount of electrons per unit volume of unit, so per meter cubed. Okay, so charge density, yeah, is the number. So I could just write number of electrons per meter cubed. Okay, so different conductors have different charge densities, and using this formula we're about to derive, okay, the charge density of different conductor is found. Yeah, and so what we know is, let's write down some other things we know. We know current, yeah, is equal to the change in charge over the change in time, which we saw was the number of electrons times by the electric charge E, yeah, divided by the change in time. Okay, so using this now, let's focus on working out the number of electrons. Okay, what we really want to know here is, if we know the charge density and we know a volume, we can get the number of electrons. So how can we make a volume out of our conductor? So let's put a line here. Now this distance here we need to know, okay, and this is area. Now I'm going to call this velocity. Now why am I going to call that velocity? Okay, this is going to be the velocity of an electron, and this distance here, okay, distance traveled in 1 second. And so anytime something is moving with a velocity, that's distance traveled in a second, meters per second. So if it was 0.5 meters per second, this distance that's traveled here is actually 0.5 meters, okay? And so we have a change in time down the bottom over here. So if we make that just 1 second, okay, or 2 seconds, it's going to change with the velocity. And so we get our volume then, okay? If we take this area, okay, volume is going to equal that cross-sectional area, which is pi r squared in this particular case, times by the velocity, And if we know the volume, we can get the number of electrons is going to equal the charge density, which we can call D, times by the area over V. So we're calling the charge density in this particular case here D. And so we get the density of charge, the area. That's the number of electrons. So if we go back to our other formula here that we're deriving, what we get then is the current is going to be equal to the charge density times by the volume times by the velocity, times by the number of electrons. And what we see is that time has disappeared because we've looked at it over 1 second. Okay, when we took this was the distance over 1 second. Okay, and so we've replaced the volume with, instead of having it A times D, what we've ended up getting is we've ended up, so over T, that became A over V. So this change in T has disappeared when we put in the V there and use that as a D. Now, so the equation we have is current is equal to the charge density times by the cross-sectional area multiplied by the drift velocity times by the elementary charge. Now, we were interested in this particular case to find the drift velocity. So the drift velocity was equal to current divided by the charge density divided by the cross-sectional area divided by the elementary charge. And that would give us the speed at which an electron is moving. So let's put this into context. Let's use this. So the drift velocity of a household circuit. What we usually work on is that the cross-sectional area, okay, is usually about, the radius is about 2 mil radius, yeah. We're usually looking at a current, somewhere between 0.5 amps for most, that's just an approximate, but that's still quite a bit of current. What we know is that we don't know the velocity, we're trying to find that out. The charge density for copper, if you look this up on the internet, is 8.5 times 10 to the 28, and that's, electrons per meter cubed. And the next piece of information that we probably would need to know, looking back at our formula, is, of course, the elementary charge, which is 1.6 times 10 to the negative 19. And so that the drift velocity was going to equal to the current divided by A D E. And if we put all that information in, the current is going to equal to 0.5. A is going to equal to pi times by 2 times 10 to the negative 3 squared times by the charge density, which is 8.5 times 10 to the 28, massive amount of electrons per meter cubed, times by the elementary charge of 1.6 times 10 to the negative 19. And if we put that into our calculator, we get 2.9 to the two significant figures times 10 to the negative 6, and this is meters per second. So, as discussed, pretty slow in terms of a speed. So, what have we learnt? So, we've gone back and we've looked at what flow is of electric charge and how we call that electric current. We've spoken about what is an electric circuit. One thing I forgot to mention with the electric circuit is an electric circuit needs something to push it, right? It needs a force, needs a potential difference. I don't know if I mentioned that in those slides. Current will flow between 2 points of a conductor if there's an electric potential difference between those points. Okay, current is carried by discrete charge carriers. Current will flow in the circuit only when the circuit forms continuous closed loop. So we spoke about the loops having to be closed, otherwise they're becoming a capacity, a build-up of charge and repulsion forces in the other direction. So when electric current flows, electrons move towards the positive terminal, and this is called electron flow. So it's the opposite direction to conventional current flow. So, and the conventional current flows in the opposite direction as we spoke about. Yeah, the current is dependent on the speed of the charged particles, the number of the charged particles. And we spoke a little bit about drift velocities there as well. And so current is equal to the number of charged particles being electrons times by the charge on an electron divided by time. And it's measured with an ammeter along the same path. So have a look at the web page, go over the slides, read the chapter, do the extra work, which are extra questions, and play with any simulations that are relevant.